Good morning. My name is Jim Fawcett. Today we're going to talk about C++ models. Here are a couple of dictionary definitions about models, and it reflects pretty much, the way we're going to use models for this presentation. So, a description that can help you understand how a system or process works. That's what we're after. On my website, I developed a C++ story, a fairly detailed walkthrough of the C++ language, and its first chapter focuses on 7 models that I think help make people understand how the language works reasonably well. So nice way to start with the language, or when you're refreshing your knowledge of the language. So in this video, we're going to talk about code structure, and we'll pick up with some of the other models in later videos. They'll be coming soon. If you want, you can pull up the slides, or here at this link. You can just pull them up and follow along as we talk if you wish. Okay, so C++ is a ambitious language, a large language. I like C++ very well. I've developed in C++ for many years. I started in 1988, and I developed code in several different languages, and of those, C++ is my favorite. So, but it is big, and takes a while to get your arms around, and models help us understand the language. And we'll see, once we're comfortable with the models, that the language is really quite internally consistent. It's a very nice design. I like it. And the models help us, use it effectively. So these models cover code structure, compilation, execution, use of memory, classes in the C++ object model. That one particularly will be a big help getting your mindset and where it needs to be, and templates. So what we're after is to help you develop this internal mental model of what the compiler is going to do. You write a line of code, what's going to happen? So it's that mindset that we're trying to help you acquire. Okay, so code structure. So we write code. When we develop code, we write it in files, of course. And but as the software systems that we develop get large, and they, a lot of them do. From my website, you'll find quite a few large projects. They become hard to understand just looking at the files. So in order to support readability and maintenance, we create what we call packages. Packages consist of a few files, and each package has a single purpose and documents the purpose and its design in comments. So files are units of construction, and packages are units of documentation. The C++ build system doesn't know anything about packages, but it does recognize projects, and we tend to associate a project with a package. Each of the packages that I develop, I almost always create a project for that package, and that helps me in the construction process, as we'll talk about that in a little bit. So packages they're just simply groups of files, one or more files, stored in a single directory, annotated with comments to help support understanding and test and maintenance. And the directory has a project for building the source code. Packages. So packages are units of documentation and translation. And each one will have a Visual Studio project, or could be if you're using G++, that would be G++ in a makefile, perhaps. So package consists of a CPP file, package name.cpp file, that has a construction test main function. We'll come back to that again in the next slide. It has a header file, package name.h, so the same name, and optionally may have an interface file, iPackage name.h. And of course, you know, package underscore name stands for whatever name you're going to give the package. Blocking queue, for example. These parts are embedded in a directory with a project file or a make file that we use that to build a construction test. And it may include files from other packages. So this package may depend on other packages. And so there may be other files in that directory. But an alternate scheme that works well when things get large, it works a little better to build the various packages as libraries. And then when I'm working on this package that depends on, let's say, 2 other packages, I make a reference to the libraries for those 2 other packages instead of loading all their files into my project directory. So again, each package is expected to implement a single responsibility and have comments that describe its operation. Okay, so let's think a little bit about testing, construction, what I call construction co-tests. So co-test is something like test-driven design, but not quite the same thing, but the intent is very similar. So for anything other than really simple example code, it's useful to have a test, and we want to test as we go. We add a main function for every CPP file, and every time we add a few lines of code, we're going to add small tests in that main, build it, and execute it. So that leads to a whole cycle of very small add, build, execute, add, build, execute cycles. And so this process allows us to find errors very quickly. If something fails, there's an overwhelming probability that that failure is going to be in the last few lines of code we entered, almost probability 1. So it makes saves a whole lot of time finding errors and fixing them in your code. And, you know, there's a lot of information in a source code for a big design, and so you know there are going to be initially some errors, and we need to fix them. And this is a great way to stay on top of that process and make the process as easy as possible. The main we wrap in if-def preprocessor directives, and you know if-def and end-if directives. And the idea here is that if we define test underscore name, where the name is the name of the package, we'll compile that main, and we can run it and observe what happens. You know, it's part of our construction test. When we're done with the package, when we think it's complete, we can run it without defining test underscore name, and now the compiler won't build that main. So now we can combine this package with other packages to build a bigger executable. You know, an executable can only have one main. So if we put mains in every one of these packages, which I do, then they need to be turned off. All but one of them need to be turned off. And we do that simply by not defining test underscore package name. It's a really simple process, and it works well. Okay, so let's talk about code structure. So here's a little example I put together that has 3 packages: an executive package, a component A package, and a component B package. And I'm showing here the files for those packages and their pound include paths. So executive includes iComponent A.h and component B.h, and component A.h includes this header file, and component A.cpp includes this header file. So, and the same for component B. Now, let's think a little bit about the structure. This is an interface, and component A.h is a header file that declares a class or one or more classes for component A, and component A, CPP, implements those classes by providing code for its methods. And the same thing is true of component B. There's a very, very typical structure. So we have an executive that orchestrates the processing flow, and we have some packages that some of them may need to talk back and forth, and so we're trying to illustrate how that works with this example. There's example code in the repositories, in this CPP story repository, and you'll find code for this along with lots of other code. You'll see, if you look at it, that there's almost no functionality in this demo. What we're trying to do, we've stripped away all the operational stuff, and all we're trying to do is illustrate how the pieces come together, how they form, how we can form a composite entity out of these separate packages. So let's take a look at this. So this will give us a little better idea. So these are the classes that are embedded inside that package. And so in component A, we have an interface component and the component itself. So this is the component's interface and the component itself. Here's an executive class. Here's a component B class, and a component B class uses a helper class. And this note, let's talk a little bit about this notation. So this triangle says that component A is implementing this interface. So the interface declares a contract for the component, but doesn't provide any of the definition. All those definitions are in component A, and there's a reason for doing that. We'll get into in just a minute. And this is a composition. So executive composes component B. That means component B, an instance of component B, is a data member of the executive class, and the helper class is an instance of the helper class is a data member of component B. These are very strong ownership rules, ownership relationships. What that means is that when executive is constructed, its constructor, as its first action, invokes the constructor of component B, and component B's first action is the first action of its constructor is to construct helper. So all of this happens as a unit. When executive is constructed, all these parts are constructed. So this is very strong. These are component B is an indelible part of executive A. Now these hollow diamonds, this is a different relationship. This is a relationship called aggregation. This is composition, this is aggregation. Aggregation is a weaker ownership relationship. It says when executive is constructed, there isn't an existing component A yet. The executive will create an instance of component A if and when it needs it. May never need it, never construct it. And the same for component B. Typically, that means that an instance of component A resides on the native heap, and component B and executive hold references to that object on the heap. And these will be smart pointers. Standard unique pointers are very typical that give the executive and component B access to component A. Now, the important thing is that these guys get access to the interface, not to the implementation details. Now, in truth, component B, for example, that pointer binds to a component A object, but it's typed as an interface component A, meaning component B can only do the things that this contract specifies, and it doesn't see any of those implementation details of component A. There's one other little bit of that recipe, and that is that this component A interface declares a factory function that executive and component B will call to create an instance. And in component A's implementation, after the component A class is declared, this class, then the factory function is implemented. That implementation has to see the declaration of the component A class before it will compile. But so that organization, the interface has a declaration for the factory function, and the component A defines the factory function after it's defined its primary class, the class that the factory function is going to create. Okay, so one thing we might mention is that C++, I talked about this as an interface. C++ doesn't have an interface construct. C# and Java do. C++ doesn't, but we use structs with functions with no definitions. They're called pure virtual functions. That struct with pure virtual functions plays exactly the same role as an interface does in C# or Java. It works very well. Okay, so here's a little bit about what's in that interface. If we look at this component A, it has no implementation. What the executive and the component B see, they see this struct declaration of the contract, the interface, and it sees a function equals 0, says this is a pure virtual function. It says this interface is not going to implement this function. It's implemented by any class that implements the interface. And here is a declaration of a factory function, create component. So what's going to happen when we call create component, we're going to get back a smart pointer pointing to a concrete component in a native heap, but it's typed as an interface, meaning this pointer can only call functions defined in this interface. And this has no information. As you can see, there's no information about what classes implement this, what are their details. None of that information is here. And that means that the executive and component B have a very strong isolation from the details of component A. So we can change component A all we want, as long as we don't change the interface and the declaration of the factory function. Executive and component B build just fine. No matter how we change this, they'll build just fine because they've been isolated from the details of component A. That turns out to be a very, very important thing that software developers do. One of the problems with large systems is that they tend to get creeping dependencies that make things hard to manage. And by using these interfaces, we break those dependencies. Now, these other parts depend on an invariant interface. They don't depend on this thing that's changing. So every time we change this, we don't have to go and change these guys because they depend on that invariant interface. One last comment before we finish. There's actually a couple of kinds of interface factory functions. So this is the kind we used in this demo. We return a unique pointer, typed as an interface, and that's pointing to a concrete instance on the managed heap. But we could also build a singleton factory that returns a C++ reference to a static instance, and that would probably be in the stack somewhere, but it's a static, so the instance itself sits in static memory, and we'll discover that means that instance will live for the duration of the program. We'll see that when we talk about our memory model. So anyway, that's the idea. Interfaces. Let's hide this panel so you can see this. So the executive and the component B are isolated from these guys, and that comes because we have an interface and we have a factory function. So this was all just a very trivial, do very little kind of demo, just to show you. You can look at the code, it's simple, and see how things are glued together. There's a more realistic example in this repository. I built a logger that I'll be using in lots of testing in the repository. And this logger uses both, actually implements both of these kinds of factory functions, so that a user to be a logger can either have a singleton instance he shares with other parts of the program, or it has one that he's just using now. All right, in the next video, we'll talk about C++ compilation models. And so I thank you for your attention, and maybe we'll see you again in one of the subsequent videos. And with that, we'll say goodbye.